So we have nuclear chemistry, and nuclear chemistry involves radiation and radioactivity. And what is radioactivity in the first part? Radioactivity. It is the breakdown of atomic nucleus. Now, when you have the atomic nucleus breakdown, it produces atomic radiation or particles. And so there are four different kinds of particles that we generally concern ourselves with. And we have, first thing that we have, and we need to know the symbol, the name, and what they are. And the first thing we have was what's called alpha. And alpha radiation is an atomic nucleus. It is a helium nucleus, and it's symbolized with a funny looking A, just like that. And it's a helium 4-2 nucleus. And there's no electrons on it. It's just the nucleus. And so another kind of radiation that you can have from radioactive decay is something called a beta particle. And it's a funny looking B, just like that. And its symbol is a funny looking B, but a beta particle is actually an electron. And so usually what we say is it's an electron, but we're going to put the -1 charge on the lower left instead of the top right. And the atomic mass, which is the number up top, is 0, because after all, an electron has practically no mass. And so the -1 represents the total charges that you have, and it's a -1 charge, and it has a mass of essentially 0, and it's an electron. Now, this electron that comes from the radioactive decay is not one of the electrons on the outside. It actually comes from the decay of a proton into a neutron into a proton. That's what happens. Okay, and then we have what's called positron. Now, a positron is an anti-electron, or an opposite to the beta, and we symbolize that with another funny looking B, where we're going to put a plus on it to show that it is a positively charged electron. And it's still an electron, but it has a +1 charge and a mass of 0. And many times we'll actually symbolize it with the beta, just to be clear, and we say that's a +1 right there. And then we have gamma, which is not a particle at all. It's a kind of form of light that's more energetic than, say, X-rays. And we give it the symbol that looks like this. It's kind of like those ribbons that people wear. And since it's a particle of light, it has no charge and it has no mass. And this is like X-rays, except more powerful. But way more powerful. Or energetic is another way of saying it. So out of these four particles, gamma rays are the most powerful out of all of them. These are the most powerful. Okay? And so when we have these particles and we're producing radioactive decay, we need to be able to protect ourselves from radiation. And there's 3 different ways of protecting yourself from radiation, and we have to memorize this. So everything on here you need to make flashcards for and memorize them. So protection. What do we do to protect ourselves? Well, the first thing that we can do is shielding. And that means to put something between you and it. Okay? And protection depends on the kind of radiation that you have. And if we look at this list over on the left-hand side, what kind of protection do you need? And generally, for the first three, alphas, betas, and positrons, you generally just need a thick lab coat and gloves. But for gamma, you need thick concrete or lead. To protect yourself. This is the kind of shielding that you need. Now, if you've ever had an x-ray, and most of us have, especially if you go to the dentist, they want to take pictures of your teeth with x-rays, you'll remember they put a lead vest on you, and that's shielding. And gamma requires considerably more lead than the lead vest that you have when you go to the dentist, because gamma rays are like x-rays but much more energetic. So out of the four, gamma rays require the most shielding, thick concrete or lead, whereas the other ones you can get by with a thick lab coat and gloves. Now, the second way that you can protect yourself is distance. Further away, less radiation. Just get away from it. And so, once again, if the technician is giving you an X-ray in the dentist's office, well, what do? Not only do they step behind a barrier so they don't get zapped and they put lead on you, a lead vest on you, but they also step away. They step away because that's distance, and distance will protect you from radiation. And the final way of protecting yourself from radiation or radioactivity is time. Spend less time. The less time you're exposed, the less radiation that you have. And so, if you're working around radioactive materials, one of the things that you have to do is you have to wear a device to tell how much you've been exposed. And the more you're around radioactive material, the more exposure you're going to have. So all of this here is very much flashcard worthy. You need to memorize the symbols with the name, and you also need to know the three ways of protecting yourself from radiation. Now, we need to be able to do nuclear reactions is what we need to be able to do. This is our skill. So we have what are called nuclear reactions. Now, the real key to doing nuclear reactions is that we have tops and bottoms. We have the atomic mass and we have the atomic number, and we have to get them to be the same on both sides. And let me show you what I mean. So let's do an alpha decay. All right. Alpha decay means that we are producing a 4-2 helium, because that's an alpha particle. Okay, that means that you're producing it, means you're going to be on the right-hand side of an equation. So let's alpha decay uranium 235, and we look on the periodic table, and it's element number 92. And of course, to remind you, the 92 means protons, and the 235 means the atomic mass number, which is the protons plus neutrons. And if we're going to decay, then we draw an arrow, and we say we're going to produce a 4-2 helium and something else. So we say plus something else. That's what an alpha decay looks like. So what our goal here is to figure out what is going to be this product in addition to the alpha particle. And so the uranium-235 is breaking down into an alpha particle and some other element. Okay, now the key is going to be that we want the tops. We want the tops over here. This is the top. Here's the other top. And here's my unknown element. And I want these tops, the 4 plus whatever it is, which I don't know yet, and the bottoms, 2 plus something, is going to equal whatever's on the left-hand side to 235. So what can we do? So erase this. Let's do the top first. And so we say 4 plus something gives me 235. And so 4 plus what gives me 235? And that would be 231. So now the tops, or the atomic mass numbers on the right-hand side, equal the atomic mass number on the left-hand side. And so we do the same thing for the bottom. We say what? Plus 2 gives me 92, and we say 90. Now we have to look at the periodic table and find element number 90. And where is 90? And we look, and if you look down on the bottom left, you'll see TH, which is element number 90, and that's thorium. And so we say, well, this is thorium. So the product of alpha decay of uranium-235 is thorium-231. Now we can take that thorium-231 and we can do another alpha decay if we want. So let's do an alpha decay of the thorium-231. Now keep in mind, these elements that we have in these reactions may or may not be naturally occurring. Uranium-235 is naturally occurring. But if you look on the periodic table, uranium is 238 for the weighted average of all the isotopes. So you see, don't go by what it says on the periodic table. The only thing on the periodic table that you're going to go by is the element number. So don't try to fix the top number and make it match up to the periodic table, because that's not what's on the periodic table. So let's go ahead and alpha decay this thorium-231. And so once again, we say it's a 4,2 helium, since we're doing alpha decay for both of these, and plus something. And by the way, it doesn't matter if you put the helium first or you put the helium second, it doesn't matter. And so what do we have here? So say what plus 4 gives me 231, and that would be 227. 227 plus 4 gives me 231. And then we say what plus 2 gives me 90, and that would be 88. And so we look on our periodic table and we find element number 88. And we look and we see that element number 88 is, where is he? It is Ra, radium. Ra, radium. That's element number 88. And so we dutifully put down Ra. So whatever their product is, you do have to go to the periodic table and find it. And you match that number that's on the top of the element, and that's the element. Now for beta decay is a little different. And so this is why we have to memorize our atomic symbols for the particles. And beta decay, well, that's an electron that comes from the nucleus, from the decay of the nucleus, and it looks just like that. It's a -1 on the bottom and a 0 on the top. It has a -1 for the charge. There's no protons. And it has a 0, or essentially 0, for the mass. And so that's our beta particle. So if we're going to beta decay something, let's say let's beta decay chlorine 39, and that is element number 17 for chlorine. And if we're going to beta decay it, what does that mean? That means that we're going to produce a beta particle plus something else. And so we look at this and, let's do the top first. And what plus 0 gives me 39. Of course, anything plus 0 is still the same number, so the top was easy, 39. Now, how about that bottom? Now, the bottom, you have to be careful, and it's real easy to mess up a beta decay, because you have to understand that minus means you're subtracting. And so it's a common mistake to say, oh, well, 1 plus 16 gives me 17. No, you're not adding 1, you're subtracting 1. So this actually becomes 18. So 18 minus 1 gives you 17. And so what is element number 18? Well, it's the next one over, and that would be argon. So the product of beta decay of chlorine 39 is argon 39. And if you notice, the tops didn't change. The atomic mass of these two elements is the same, but the number of protons is different. And of course, the atomic number of protons tells you what the element is. The top number depends on what isotope it is. Okay? And so we can go ahead and let's beta decay that argon 39. We can do that. And this is the way reactions usually work too. They go in chains. Something will decay to something else, and then that something else decays to something else again. And so let's beta decay this. And so once again, if it's beta decay, it means you're producing an electron, a 0 minus 1. And by the way, we could write, it as a beta particle. Let's do that. This means exactly the same thing. I'll just replace that with a funny looking B. It means exactly the same thing. When I'm doing these, I'll go back and forth depending on just what I'm looking at. And so let's beta decay this. And once again, the top's not going to change because 39 plus 0 gives me 39. And we have to be very careful that whatever subtracted from gives you 18. And of course, that would be 19. And we look on our periodic table and we find element number 19 is potassium. And this would be potassium 39. And in fact, we could go ahead and continue this chain, but how about let's do an alpha decay of this same isotope. And so let's do an alpha decay of potassium 39, because this is the way it works. You'll have some alphas, you'll have some betas, and you'll have some alphas and betas until you become a stable nucleus, which is not radioactive anymore. And since I want to do an alpha decay of the potassium 39, that means we're producing a 4-2 helium plus something else. And in this case, we go, well, 4 plus 35 gives me 39. And then we say 17 plus 2 gives me 19. And I look for element number 17, and we're back to chlorine. Now, if you look back up here, what chlorine did we start out with? We started out with chlorine 39 at the top. We did a beta decay, another beta decay, and then we did an alpha decay, and now we've come down to chlorine 35, which means after these three reactions, we have another isotope of chlorine, which has 4 fewer neutrons, because the number of protons is now the same, 17, but 35 and 39 means you're missing 4, which is the 4 neutrons. And so this is the way radioactive decay works. You're going back and forth between alpha and beta decays typically. And so we could beta decay this again. Let's beta decay this chlorine 35. And that would mean, since it's a beta decay, a 0 minus 1 beta particle or electron plus something else. And we have 35, 18, and once again, we're back to argon. And you can do this, and as you go back and forth between alphas and betas, this is what happens naturally, is that the particles will have a tendency to just kind of run down. They'll just kind of run down from one to the next. So, you start out, say, chlorine 39, and then down you go to a more stable form, which would be chlorine 35. And in the meantime, you're producing particles that are coming out. You got electrons and more electrons and beta particles and so forth as you run down this decay chain, eventually settling down on a stable isotope, which would be this guy here, stable. It probably wouldn't beta decay from that point, but that's how you do it. You have to make sure that the tops and bottoms add up. And so we can do some more. Let's say we want to do a positron decay. Well, it's the same sort of thing. let's take some radioactive iodine, and I'm going to say iodine 127, and iodine is element number 53 from our periodic table. And let's say I want to do a positron decay. And we look at our table, or we've memorized this, and we see the positron is a positively charged electron. In other words, instead of a -1 charge, it has a +1 charge. And it's still, since it's an electron, it has a mass of essentially 0. And so let's positron decay this. And what that means is any sort of decay, we just draw an arrow and we take a look over here and we go, well, all right, well, that's an electron and mass is 0. It has since it's a positron, it's +1 plus something else. And so once again, the top part's easy. 0 plus something gives me 127, and that would be 127. And this time, since it's a +1, then we would have 52 plus 1 gives me iodine. And so now we look on the periodic table, we find element number 52, and it is Te, tellurium. And so we can go ahead and beta. Let's alpha decay this. So we can alpha decay the tellurium, and 52 goes to a 4,2 helium plus something else. And once again, we just make sure the tops add up and the bottoms add up. And I look for element number 50, and element number 50 is Sn, which is 10. So that's 10, 123. And we can do this all day long as far as the decays go. And gamma, which is radiation, you're actually taking an element that is excited, such as technetium, which would be